Welcome to the book, A Ray of Light, a book of science and wonder by Walter Wick. And you may have remembered the other Walter Wick book that we read called A Drop of Water. So this one is A Ray of Light. And it says, for Linda, this quote says, "And yet how little even the wisest among us know about the nature and work of these bright messengers of the sun as they dart across space." And Arabella B. Buckley said that in The Fairyland of Science, 1878. What is light? Everything from the earth beneath our feet, the water we drink, and the air we breathe is made of atoms. Atoms are the tiny, invisible building blocks of matter. Matter can be a solid, liquid, or gas. Matter is the basis of everything we see, feel, smell, or touch. What about light? What is it made of? How does it fit alongside everything else in the world? Light is energy. Rub two hands together rapidly, and the friction will warm your hands. Strike a wooden match across a rough rock, and the friction will cause the phosphor-tipped match to burst into flame. The flame will radiate energy in the form of heat and light as long as there is wood to burn. Although light is neither a solid, liquid, nor gas, all three kinds of matter can have a role in its creation. Our match has lit the candle, and the melting wax travels up the wick and provides more fuel to the flame. The flame is a violent storm of hydrogen, carbon, and oxygen atoms, large clusters of them breaking down into smaller clusters, releasing energy in the form of heat and light. Incandescence. Light that comes from heat is called incandescence. A burning candle, red-hot metal, the fiery sun, all are forms of incandescent light. At left, a trickle of electricity heats the metal filament. So we're talking here. Heats that coiled metal filament, emitting a soft red glow. As the temperature of an incandescent light source increases, the color of the light emitted shifts from red to orange to white. The color shifts below are due to the increasing temperatures of the corresponding light sources pictured above. Fluorescent, sodium vapor, and light-emitting diodes, or LEDs, are some of the many types of light sources not produced from heat substances, so their varying color tints are not connected to temperature. However, all light, no matter how it's produced, is the same form of energy called electromagnetic radiation, traveling at the same blazing speed of 186,000 miles per second, a speed so fast that the light from the sun, 93 million miles away, took only 8 minutes and 20 seconds to reach the spoon below. So I know most of us don't have incandescent light bulbs anymore, the ones that look like this. They get really hot. We now have light bulbs that are way more energy efficient than these, and they don't let off as much heat, because when we turn a light on, we're not looking for it to heat our homes. We're looking for light. So the ones that we have today do not let off as much heat, but they do have things inside of them that we have to make sure that we're being very careful with them, because if they break, it can cause some problems. So you have to make sure you properly clean up any broken light bulbs. Okay, let's go on. It says light waves. Light travels in waves. Because waves of all kinds share similar behaviors, we can look to water waves to help us understand the wave behavior of light. Above, a ball attached to a rod vibrates at different speeds, slow, medium, and fast. So you can see slow, medium, fast. The crest of each wave represents a pulse of energy radiating out from the vibrating ball. The distance between neighboring crests is the wavelength. So the crest is the top. So the little part between is the wavelength. If we think of the ball as a single vibrating atom, we can imagine light waves emanating from it. Light waves cannot be seen directly. Instead, waves are sensed by the frequency of the waves, pulses hitting the nerves at the back of our eyes. Longer wavelengths are lower frequency waves and are perceived as red. Turn up the frequency and the color changes. Medium wavelengths are perceived as green. Shorter wavelengths are perceived as blue. Light waves are not only very fast, but also very small. A distance equal to the width of this pinhead would contain about 6,500 wavelengths of red light, 7,000 of green, and 9,000 of blue. The ability to distinguish these colors is due to our brain's amazing ability to sense the differences between these extremely fast and very tiny pulses of energy. However, if the distinctly different red, green, and blue wavelengths of light overlap, as we see above, the colors can no longer be distinguished from one another. What we see instead is white light. So did you know that if you overlap the different colors of light, you'll end up with white? White actually reflects all colors of light. A light obstacle course. Unless obstructed or reflected, light travels in perfectly straight lines. Above, a ray of sunlight comes in straight from the left. Encountering a clear water-filled box, head-on, the light remains perfectly straight as it passes through. Arriving at the next box at an angle, the light bends down slightly, then bends up again, continuing on a straight path. The bending of light rays by plastic, glass, water, or any other clear substance is called refraction. As fast as light travels, it slows down when it's going through clear substances, then resumes its faster speed upon entering the air again. Refraction can occur at any point where such speed changes occur. In the example above, refraction is seen at both the air to water and water to air points of the angled box. So see when it's going from the air to the water or the water to the air. At the same time, a portion of light is also reflected from those points. One of those reflected rays is also refracted again as it exits the box at the top. So it is reflecting, but it's also refracting or bending. When the sunlight enters the triangular box at an angle, the light also refracts downward, just as with the angled rectangular box. But as it leaves the triangle, it angles farther down again. In doing so, you can see that the sunlight has begun to split into its component colors, with those colors appearing even more distinct and vivid at the far right of the picture. The shorter wavelengths in the blue-violet range of color bend the most, and the longer wavelengths of red light bend the least. All other colors fall in between. So can you see those colors? You can see the rainbow there, or the spectrum. There's the color spectrum. There are perhaps no colors found anywhere on Earth as brilliant and as vivid as those found in sunlight, refracted by a simple glass prism. It should be noted that a photograph, especially those reproduced in a book, cannot fully capture the purity and intensity of color, that's observed directly by the human eye. Here, the full range of the sun's colors are spread out on a piece of paper that has been placed in the path of refracted light. That range of color is called the color spectrum and includes all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Each color in the spectrum has a different wavelength and can't be further split by refracting it through another prism. The color spectrum is the visible portion of a much wider range of electromagnetic radiation. Just beyond the red end of the visible spectrum lies infrared light, which is sensed through our skin as heat. At the other end, so here's the infrared. At the other end is ultraviolet light, which, due to its shorter wavelength, transmits higher energy levels that can damage skin. So you probably wear sunblock that helps block UV rays. That's those ultraviolet rays that we're talking about here. A vanishing color trick. Overlapping red, green, and blue light will appear as white. But what color is made from overlapping just red and green light? If you're used to getting brown from mixing red and green paint, you may be surprised. Red and green light make bright yellow. So you can see red and green right there. Mixing green and blue light makes a light blue-green color called cyan. And mixing red and blue light makes magenta. We now have the basis for a vanishing color trick. Below, two colorful tops on the left are shown, spinning on the right. Where did the color go? Equal amounts of red, green, and blue, or equal amounts of cyan, magenta, and yellow, will result in gray in the spinning tops because no one color dominates, and the eye can no longer discern separate wavelengths when mixed by the rapid motion. A similar trick is employed in the printing of this book. Though white is obtained from the paper itself, a magnified view of the grays in the tops will review a pattern of tiny dots of cyan, magenta, and yellow. By adjusting the balance of those three colors, all the other colors in this book are formed. Digital displays also work this way, except the three base colors are red, green, and blue, and white is obtained by brightening all of those colors at once. Well, this looks like, in the book, Drop of Water. Iridescence. To the right is a wire frame that has been dipped in a solution of soap and water. Why do we see colors in what is otherwise a clear, colorless liquid? A clue can be found in how objects reflect off both the front and back surfaces of any clear substance. Soap film becomes extremely thin as it evaporates. As the film thins to dimensions approaching the wavelength of light, wave crests reflecting off the front of the film overlap with wave crests reflecting off the back, much like the overlapping pin reflections on thin glass above. If the double reflection of wave crests of any given wavelength perfectly align, that wavelength's color brightens. At the same time, wave crests of other wavelengths will misalign, inhibiting our ability to see these colors at all. This combination of alignment or misalignment of wave crests is called interference. The resulting shimmering color is called iridescence. The varying swirl of brilliant colors is due to ever-changing thickness of the very thin film. Where else maybe have you seen iridescence before? Nature's shimmering color. Certain feathers, butterflies, beetles, and shells are examples of iridescence found in living things. Although they may have underlying colors of brown, black, or white, their bright shimmering surface colors are due to light interacting with microscopic ridges embedded in those surfaces. When light strikes those tiny ridges, a form of interference occurs. Certain wavelengths double up and brighten, while others cancel out and weaken, much like what we've seen with soap film. Rainbows are another way nature can split sunlight into its component colors. Because raindrops are spherical, their round shape acts like a lens, focusing a bright spot of sunlight onto the back of the drop. At a certain position in the sky, those bright spot flash colors of the spectrum due to the prism-like refraction occurring inside the drop. Shimmering bright lines of rainbow colors can also be seen at the fringes of refracted light at the bottom of a shallow pool. Pigments. Dazzling as the iridescent soap bubble or refracted rainbow are, those colors can flash brilliantly or fade away depending on the angle of the sun, the position of the viewer, and other factors. Fortunately, much of the color we encounter in the world is due to more permanent materials called pigments. From fruit to flowers, from balloons to billboards, pigments produce color by absorbing some wavelengths while scattering others back toward your eye. Chalk is a white pigment because the calcium and oxygen atoms it's composed of scatter most wavelengths. Charcoal is a black pigment because its carbon atoms absorb nearly all wavelengths, converting that absorbed energy to heat. Pigments, along with related liquefied colorants called dyes, can be derived from plants or animals. Many are extracted from the earth. Still others are made from synthetic chemicals. Though the chemical composition of pigments can be complex, grinding them into fine powder doesn't change how their internal atoms interact with light. The blue pigments above absorb most wavelengths but blue. The yellow pigment absorbs most wavelengths but yellow, even though they are both illuminated by the same light. Suspended in a clear medium such as oil or water, pigments are made into paint and can be further mixed to make many other colors. So what wavelengths are absorbed by for the red? Everything but red. Red is actually reflected. The lens. Sunlight is powerful. Streaming in a window, you'll feel its warmth. But when a beam of light just 5 inches wide is focused by a simple lens, the pinpoint concentration of all that energy will cause a match to burst into flame in a matter of seconds. The human eye refracts light in the same way, which is why you should never stare directly into the sun. The concentration of sunlight will do serious damage to your eyes. The device used here is an ordinary magnifying glass, but used in this way, it's a burning lens. Children should be closely supervised when conducting any experiments involving a burning lens. Oh, look at this picture. The lens above, also an ordinary magnifying glass, is acting much like the human eye, projecting an image of a candle on the wall. The image is upside down, but then so are the images projected onto the back of your eye. Your brain does the work of correcting the upside down image. Though the candle flame is way too hot to touch, very little heat can be felt through the flame's projection. This arrangement of lens and projection is also the basis of all cameras, whether for stills or video, film or digital. Though such cameras require additional lens components to improve image clarity and an enclosure to prevent stray light from washing out the projected image. You see how that flame is upside down? See the candle? Seeing the unseen. Simple magnifiers made from lenses have been in use for thousands of years. About 400 years ago, a new way to use those lenses began with the invention of the microscope and telescope, revealing previously unseen wonders, minute structures of plants and animals, mountains on the moon, and new objects in the heavens. Early microscope lenses were shaped from tiny drops of melted glass, but the lens of the simple microscope above is made with a drop of water suspended in a brass washer. Suspended in a brass washer. A liquid lens isn't as practical as a solid glass one, but its steeply curved shape is what enables the lens to focus close in on the slice of sunflower stem, seen here enlarged to 15 times its actual size. So did you catch that? They used a little metal washer here, and they put a drop of water on it, and it's magnifying this sunflower stem, so it's making it look larger. So yeah, water can be used. I bet you've noticed that before, that things look bigger in water. All right, we're going to read here. A telescope capable of revealing mountains on the moon can be made with two simple lenses. Above, the nearest lens, called the eyepiece, is a strong magnifier bringing light to focus over a very short distance. The furthest lens, called the objective, is weaker and brings light to a focus over a larger distance. This design, usually constructed with two telescoping tubes to hold the lenses, is called a refracting telescope because of the light-bending function of the lenses. The discoveries made with these new optical tools astounded early scientists. Like the examples shown here, early devices provided clarity only in the central portion of the image. But with patience and gradual improvements of the instruments, details of these wonders were carefully mapped and drawn, and a new age of science began. Atmospheric light. Though the same sun illuminates our Earth and moon in equal measure, the blue skies and dazzling sunsets visible on Earth could never occur on the airless moon. Light travels fastest in the vacuum of outer space. When it reaches the Earth's atmosphere, it slows down a bit, just as it slows further when going from air to water. Oxygen in the upper atmosphere absorbs much of the sun's harmful ultraviolet light. Visible light, meanwhile, is partially scattered by various air molecules. The sky is blue because shorter wavelengths scatter more easily than longer wavelengths. When the sun is low, light must pass through much longer stretches of atmosphere, further scattering blue light, while longer wavelengths of red and orange light slip through, often bathing Earth and sky in a golden glow. The moon's weak gravity accounts for its lack of atmosphere. Sunlight, therefore, reaches its surface unfiltered, resulting in perpetually black skies, extreme temperatures, and dangerously high levels of radiation. So here's an Earth and moon size comparison. And you guys already knew that. You already knew that the Earth is bigger than the moon, and that the sun is bigger than the Earth. Speaking of the sun. The sun is so massive, 1,000,000 Earths could fit inside. Its gravity is so strong, extreme pressure at its center fuses together hydrogen atoms, transforming them into helium. This transformation of hydrogen to helium, the two main components of the sun, is called nuclear fusion, a process that results in the release of enormous amounts of energy, the visible portion of which we call light. The Earth's distance of 93 million miles helps keep us safe from the sun's ferocious heat. If the Earth were the size of the blue pin shown below, see the blue pin? Very tiny. The sun would be the size of a 17-inch ball. At that scale, a string 150 feet long would represent the distance from the sun to the Earth. If you were to place the ball at the center of a soccer field and walk around it with the pin, you would simulate the Earth's orbit around the sun. In doing so, with every step, you could sense how the Earth receives only a tiny portion of the sun's enormous outpouring of energy. This is bright messengers. Given the sun's great distance from Earth, how could we possibly know what it's made of? The answer can be found hidden in plain sight. When sunlight is refracted by a prism, we could see a continuous color spectrum. When refracted by an instrument called a spectroscope, a pattern of dark lines reveals gaps in the spectrum. While the spectrum colors represent light emitted by atoms, the gaps represent light absorbed by those atoms. Such patterns, like that of hydrogen and helium shown above, are unique to different atoms. Thus, like coded messages, these patterns carried along within light itself tell us not only what the sun is made of, but what other stars are made of too. It says this is an Earth, Sun, Stars composite. So it's got, you can see the Earth, Sun, and then the stars. Every ray of light. The last rays of summer light stream through a window. A tiny blue Earth makes its year-long orbit around the sun, a journey nearly 600 million miles long. The Earth rotates daily in its orbits, turning toward the sun each morning, turning away again at night. Each day, the Earth takes the littlest sips of the sun's vast outpouring of energy. However tiny that portion of light is that reaches us, we could not exist without its life-sustaining energy, darting across space, quivering within each and every ray of light. Here's a prism. And there's some extra information if you're interested, and you could get this book and read a little bit more about each area. And I'm going to read about this book by Walter Wick. It says, this book was conceived as a companion to my 1997 book, A Drop of Water, a book of science and wonder, although I could have not imagined then that it would take 2 decades to bring it to fruition. In those intervening years, however, I created many other books for children that have had the benefit of further reinforcing what I had already begun to see firsthand, the astounding visual acuity of young readers. Thus encouraged, I took a leap of faith that I could tackle the complex subject of light by way of tangible, concrete tabletop experiments, with the hope that the intrinsic wonders of this topic would feel as close to my readers as the book they hold in their hands. The photographs of experiments set up in my studio and environs, with the exception of a few, were made with a digital camera. Some images required combination 2 or more exposures for balancing light levels or color. Others required some localized retouching for clarity. But all are faithful to the phenomena described in the text. And that is written by Walter Wick. And that is the end of our book, A Ray of Light. I hope you enjoyed that, and actually you got a whole bunch of previews of some of the science labs we are going to be completing as we study light energy. That's it for me. Take care.
Hey,